Hey geometry students, it's Mr. Pouts with section 6-9, and this is all about coordinate proofs. So the last couple sections we've been talking about coordinate geometry, how we can use the midpoint formula, the slope formula, the distance formula, and then also how we can label different things on a coordinate plane in case we're just trying to prove a general proof and choose like how to shape the polygon on the coordinate plane. So we're going to use all that, and we're going to prove theorems in our goal here. We're going to prove theorems using figures in the coordinate plane. So we're going to start you off with a proof. This is a fill-in-the-blank proof. If you can try it on your own, I'd like you to try it first if you want to pause it, but then we're going to go on. It says it's the triangle midsegment theorem. So this is a theorem that we've already used. We're going to prove it. It says we're given triangle ABC. D is the midpoint of AC, and E is the midpoint of AB. So that's all on our lines here. And we're trying to prove that DE DE is 1/2 of CB, and that DE is parallel to CB. That's what the triangle midsegment theorem says. So we could technically, if we wanted to, put this triangle anywhere on a coordinate graph, um, anywhere that we want. But this was chosen, so I scribbled out the stuff over to the right because I want you to just visualize we can put it anywhere. Um, and the things we have to do is prove that two lines are parallel, so that's going to deal with slope. We're also going to deal with the distance here of the line um, of DE and CB. So it really does not matter at all where you put it, but this was placed on here because this makes it a little bit easier for us. Okay? It has a line, like we talked about last section, it has a side on an axis. The origin is in there, so we have zeros. And the other coordinate is also on an axis. So this we're going to deal with it this way. So this is actually fill in the blank proof. Starts you off, and this is kind of how we're going to work through some things. Part A, already given, it says find the coordinates of D and E. And by the way, um, coordinate proofs are a little bit different than regular proofs. It's not like we're going to have two columns. It's like we're going to work through a problem and show it proving that. But like for part A, it says find the coordinates of D and E. And we're going to use that, the mid formula would be kind of our reasoning of how we're finding those coordinates. So the midpoint formula of D and E, so let's do D, it's between C and A. So we're going to use these two, we're going to use these two things. So the midpoint formula is the average of the x's, so negative 2a plus 0, divided by 2. So that'll end up being negative 1a. And then 2h plus 0 would be 2h, divided by 1 would be 2h. E would be the same thing. We're finding the average of the x's and the average of the y's. This one we end up with 1h for the x would be, or sorry, it would just be a, because it's 2a over a, or 2a over 2. And then for the y would be 2h, and then be 2h over 2, which is just going to be h. Alright. Now I think there's a mistake here for D. The y values we do 0 plus 2h should be divided by 2. Ah, I found an error. So it's going to still be, it's going to actually be h right there. Alright, so they're going up the same distance, D and E for the height. Alright, now we're going to find DE and CB. So we have the coordinates for the mid segment. That's good. We're going to now find DE and CB because we're going to try and prove that DE is 1/2 of CB. So we're going to use the distance formula. It's already started off for you. For DE, we're going to use these 2 points that we used. Alright, x2 minus x1. So we're going to do A. Well, I guess we're going to do negative 1A minus A. We could also do A minus negative A. But either way, it's going to become positive because we're squaring it. So we're going to end up with a square root of negative 2A squared plus. Alright, then we're going to do the h minus h, which is going to be 0 squared. This is going to be 0. And that's going to end up being equal to Now, since there's only one thing in there, there's no addition anymore. This is gone. We can take the square root and cancel out the square root and the squared sign. So it is going to just be equal to negative 2a. This one we'll see here. This one, negative 2a minus 2a. Working with these points for C and B. That's going to be negative 4a. That's all squared. Underneath the square root. And then 0 minus 0, that's also 0. So that's all it is. Now the square and the square root can cancel each other out. We get negative 4a. And that right there proves that DE equals 1/2 of CB. Now we have to figure out the slopes because we want to see if they're parallel. Find the slope of DE and the slope of BC. All right, DE. We're going to be able to tell that they're both going to be the same slope. It's a 0 slope. But DE equals y2 minus y1 over x2 minus x1. That's going to be h minus h over a minus negative a. So it's going to be 0 over 2a, which is equal to 0. 0 slope. So the slope of BC is going to be y2 minus y1 is 0 minus 0. There we go, we have 0 on top. And 2 minus negative 2a minus negative 2a. So we have 0 over 4a, which is equal to 0. Same slopes, they are parallel. And that, they're right there. We do not have to say anything else other than we just proved what we wanted to prove. Alright? Now again, we started off, we set it up, we put the triangle there because we were able to use that easily. It says, in the proof we just completed, explain why it's easier to use coordinates 0, 2h, 2a, and 0, and negative 2a and 0, rather than 0h. So again, they're multiplied, we multiplied all the coordinates by 2, and I'm wondering why you think we did that. So I'm going to have you answer why you think we multiplied all the coordinates by 2, made it bigger on our graph than we had to for this one. Alright, I'll tell you why. If you look in the midpoint formula, if you notice, when we had 2a on the top and 2h, it all cancels out and there was no coefficients in front of any of these variables, except for the negative 1. If we would have done positive 1, we'd end up having halves, and that would be a little bit more of a pain in the butt to work with. Halves, we'd rather not work with halves. So that's why we wrote it the way we did. Oh, look, John Wayne. All right, there's a few more problems here. It says, tell whether you can reach each type of conclusion below using coordinate methods. Give a reason for each answer. So using our coordinates like we just did, could we somehow prove that two angles are the same? Yes. I'm going to say yes if we have right angles or isosceles or equilateral triangles. Because then we can prove things about angles. There's not too many times otherwise. I guess if we're dealing with, if we can prove that they're parallelograms, we know that opposite angles are congruent. There's different ways to do it, but again, we have to have certain things going our way. Can we prove that two triangles are congruent? Yes, most certainly. There's all the different ways we can do side, angle, side. We can do side, 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 especially side, side, side would be the most common way to do it with coordinates because we can find distances. How about number 5? Quadrilateral is a rectangle. Well, yes. We can prove that they have right angles if they're perpendicular. If we can prove that it's equal angular. This one's tough, unless we can first prove that it's equilateral. Otherwise, we wouldn't be able to do it too easily. If we can prove that it's equilateral, then we can prove that it is equiangular. The base angles of an isosceles trapezoid are congruent. Can we prove that? Well, if we know that it is an isosceles trapezoid, I don't know that we could prove that the base angles are congruent then. So, using coordinate proof geometry. So we're going to say no for right now, assuming we don't know that they're already congruent. And quadrilateral WXYZ is a parallelogram. Yes, slope formula. So there's so many different things we can prove using coordinate geometry. Um, so that's why it is a very helpful thing to do. All right, and we're going to actually finish up with the, well, we'll try this one. Use coordinate geometry to prove the following. A triangle ABC is a right isosceles triangle. So we have to prove that it's a right triangle. We have to prove that it's an isosceles triangle. All right, we're going to leave that actually for next time. So if you want to try to prove that one on your own, that would be great. And you can check in with me next time. Otherwise, I will work with you on that. Try it though. And then answer the closing question. How would you prove quadrilateral KLMN is an isosceles trapezoid using coordinate geometry? And that is all for right now. Oh look, John Wayne. All right, we'll see you later. Have a great rest of your day.